Thank you very much, Hossein, for the nice introduction. And of course, thank you very much also for the invitation to come here and for organizing this wonderful workshop. And actually, I have to admit, also the breaks are really quite valuable. So we've been discussing so much and in such a good way that we could even have more breaks. But let's start with the talk. Yeah? So what I'm going to be telling you about is deterministically prepared few-fermion systems. And of course, in the course of this workshop, I mean, there have been many talks which actually focus exactly on this. Atomic systems, molecular systems, they're of course always deterministically prepared. If they're in the ground state, they will always be exactly the same. Yeah? Every single implementation that you realize will be exactly the same. Yeah? So and now, what is it all special about this thing here in my talk? I hope I will convince you that there are a few things that are kind of peculiar about it. First of all, let me give you a brief motivation why we actually are interested in these kind of systems. So this is kind of ultra-cold systems that we are talking about here. What we really realize in our lab is an isolated quantum system in which we really can control all the degrees of freedom. Yeah? And that is the interaction strength, the confinement, and the motion of the particles. And you can really picture our systems to be looking very much like this cartoon here, like more or less harmonic confinement, and then the lowest vibrational levels of a harmonic oscillator filled one by one with a spin up and spin down particle each, for example. Yeah? And of course, what we would like to do here is study pairing in this system, kind of various regimes, weak coupling, strong coupling. So weak coupling, you could think of this system kind of being, if you had, like, for example, 3 up particles and 1 down particle, this would weakly pair to just the particle which is sitting in the same motional state. But if you have strong pairing, you know, this one minority particle will somehow be bound to all the other ones, paired with all the other ones, forming something that looks a little bit like a polaron. And these kind of systems can, of course, be studied with quite big flexibility and also precision in this isolated quantum system. Yeah? And of course, you can think even further and can ask the question, once you have a real isolated quantum system, you would want to see dynamics, you want to see the time evolution of such a system. And typically in ultra-cold gases, we are dealing with isolated systems, but usually we can still describe them very well as being in a thermal bath with a particular chemical potential and so on, because the systems are so large that we cannot make the difference between an isolated system and a system that's in a thermal bath. Yeah? But this should be very well possible in these finite deterministic systems that we are studying. Okay, so for the motivation, so what I'm going to talk to you about is, first of all, I'll explain you very shortly how we actually prepare these systems and what are the tools that we can use to manipulate them. And if you look at these kind of pictures here, the cartoons that I'm drawing for you here for the second part, where we study repulsive interactions between the particles, it looks a little bit like the cartoons that people from the ultra-short community draw when they draw their kind of Coulomb potentials with electrons bound in them. So we can also tilt our potentials, in our case, not with short laser pulses, but just applying magnetic field gradients. And we can look at tunneling of individual atoms out of our potential well. Yeah, and so in that sense, the physics can in many places be quite similar than the one of in the ultra-short community. And the third part will then be devoted to similar experimental techniques, but we will study attractive systems, and here we'll study correlated tunneling of particles. That's also a topic that's quite common in the ultra-short community, but we are mostly interested here in kind of analogies with nuclear physics, where you have, for example, tunneling of pairs in the sense that you have alpha decays, so alpha particles tunneling out of your nuclear potential. And what I will also show you, that we can observe a strong odd-even effect. So it depends very strongly of whether we have an odd or even number of particles in our system, how strongly the particles are bound together. Okay, so first of all, how do we prepare these systems? We start with a conventional ultra-cold Fermi gas, like many of us have this in laboratories. A typical size will be 0.1 millimeter, maybe even a little bit larger, with a temperature on the order of 250 nanokelvin, Fermi temperature half a microkelvin, so mildly degenerate gas. Yeah? So something that's relatively easy to prepare. It's actually lithium-6 atoms, but it doesn't really matter. But what we do then is we superimpose to this kind of conventional ultra-cold Fermi gas a very tiny trap, which is, in its size is in the order of a micrometer or a few micrometers, and it has a depth that's on the order of, it's also a few microkelvins in depth, so much deeper than the Fermi temperature of our reservoir ensemble, yeah? Which suddenly gives us quite a strong enhancement of the degeneracy, because now the Fermi temperature will be the depth of this combined potential on the order of 3 microkelvin, whereas the temperature is still, if we're in perfect thermal equilibrium, a fraction of a microkelvin. Yeah? And so we end up with something below a tenth of the Fermi temperature as the temperature of this combined system. And if you now calculate what the occupation probability will be for the lowest energy states in this tiny trap here, you get some value that's very, very close to 0.99949. Yeah? So that's very close to 1, so close that we cannot even measure this. And we're, of course, not limited by this process. We cannot we have no idea how to really measure such an occupation probability in the laboratory. OK, so then we remove our reservoir, and this is the sample we are studying. And so in this tiny trap, we'll have maybe something like a few hundred atoms. And now we start tilting this trap. So basically, do exactly what you do with ultra-short laser pulses. You tilt the trap and remove atoms. So with your ultra-short laser pulse, you would remove electrons, so we're removing atoms. And by tilting this trap in a very controlled way, so that's kind of a DC field that we apply, we can just choose how many vibrational levels we will keep in our potential well. Yeah? For example, in this configuration I'm drawing you here, there will be 5 vibrational levels. You would expect to have, if every vibrational level is occupied by one spin up and one spin down atom. In this case, for example, you would have 10 atoms remaining. OK, so that's kind of the idea behind the technique. So what this looks like in a classical system is shown here. So we call this kind of the classical atom culling machine. So what's done here is that's actually when you obtain your PhD in Germany, you get this nice hat with all these little things built on top of it that kind of illustrate what you've been doing during your PhD. And that's Friedhelm Savane's hat. What you see up here is a kind of reservoir with lots of atoms in it. And so you can fill from this reservoir like a tiny shot glass with atoms. And you can tilt this. It actually really works. Yeah? So there's some servos that control the motion of all these different parts. And there's also a laser that you need to focus and so on. And what you can see here is, in the end, there's 4 atoms remaining now in this case if we tilt the potential back. Yeah? And so that's basically the classical way of doing things. But of course, we are interested in the quantum world. So that is a little bit more difficult than this. But it's not so much more difficult. So what you can see in the real experiment, what's plotted here is a histogram of many, many implementations of the same experiment, and a histogram of the fluorescence that we measure in a magneto-optical trap after we prepared such a system. And what you can see, there's a distinct peak of fluorescence so that's the fluorescence signal normalized to atom numbers. So if it means 1, that's the fluorescence of 1 atom. And you can see that in basically unity probability, we really prepare if we want 2 atoms in our trap, which kind of corresponds to this simple cartoon picture. And we can do the same thing also for 8 atoms, for example. So you see 8 atoms. So there the fidelity is a little bit worse in preparation, but it's still reasonably good. So this really looks like this. And so we can really prepare the number of atoms with very good precision. And what you should also, what you might probably now question is whether this simple cartoon picture that I'm giving you here, just drawing simple harmonic oscillator levels, whether this is at all valid for the systems we are looking at. Yeah? And it's very well valid for one simple reason. The aspect ratio of our trap is about 1 to 10. So it's a cigar-shaped trap with a 1 to 10 aspect ratio. So this will be the axial vibrational levels here. And the first radial vibrational level will be about at the height of the 10th axial level. Yeah? So the first radial excitations will appear much higher in energy. So you really can think of this system of being a one-dimensional system with more or less evenly spaced harmonic oscillator vibrational levels. So that's really the system we are studying. Yeah? And so now I told you we can control the number of particles, we can control the motion of the particle because we can really prepare them in the ground state. And now we can also control the interactions. So for all these experiments, we have a knob that we can control the scattering length between the particles. So we can tune the scattering length between non-identical particles using a so-called Feshbach resonance. So this has been explained in many talks before. So we tune the scattering length here with the magnetic field. And there's some value where the scattering length becomes exactly 0. That's where we prepare the systems. So we know exactly, we are actually preparing a non-identical system. We know exactly what kind of system we prepare. And what you should also note that for all our purposes, identical fermions, so fermions with the same spin, they will not be interacting because we are in the S-wave limit of scattering, and the S-wave scattering length between identical fermions is 0. Yeah? So we can control the interactions between non-identical particles, whereas the interaction between identical particles will, for all our purposes, be 0. OK, so this is kind of tuning the scattering length using a magnetic field. But now I told you we're kind of in this 1D regime, and we've had a very nice talk by Vladimir in the beginning of this workshop, explaining us how interactions are modified in 1D. So basically, we have to take into account that we have some radial confinement, and then with this formula by Maxim Olshani, we can actually calculate from the 3D scattering length, we can really obtain a 1D scattering length, which basically shifts the resonance interaction strength to a little bit lower value in magnetic field. Yeah? But we can still basically access the whole interesting range of interaction strength in this one-dimensional system. OK, so this is kind of the preparation of our system. And now we really want to do some physics with this. The first thing is we study the repulsive few-particle system. So this kind of system, we tune in some repulsive interaction. So basically tune this one-dimensional coupling strength to positive values here. And so the two words that I'm giving you here is feminization. I'm going to explain to you what this means, and magnetism. And now you can ask yourself, so if you're a condensed matter theorist, most of you will tell immediately, OK, the ground state of a one-dimensional system without pinning the spins should be not magnetized. Yeah? And there are several theory papers on this, proving this. And one that I like particularly well is this paper here by Lieb and Mattis, where they actually calculate the energy of a system of n electrons in one dimension with an arbitrary symmetric potential. And they basically determine what the energy difference will be if you flip one of the spins. Yeah? And what they find is that if you have an unmagnetized system, if the total spin of the system is smaller, the energy of the system should always be smaller than the case of the spin polarized system. Yeah? So if the total spin is smaller, the energy should be smaller. That's basically the conclusion from this paper. And so you can nicely read that paper, and you can immediately understand that the proof is correct. But so we'll see in the course of this talk that there's some way around this, yeah? That we can still observe some magnetic ferromagnetic effects, even though this paper is right. OK, so first of all, what's our major tool? We basically observe tunneling dynamic out of a tilted trap. Yeah? And first of all, I'll explain to you all of this with just two particles interacting, because this makes our life much easier to understand the system. Yeah? So we put in two particles, one spin up, one spin down. We have them interact repulsively. And then we tilt the potential so much that particles can tunnel out of the trap. And from the observed tunneling timescales, we then can infer the total energy of the system. So this looks kind of like this. This is a measurement where we plot here on the vertical axis the mean observed atom number. So remember, every time we make a measurement, it will be an integer number of atoms, because we can simply count atoms. So this is always the mean of many, many measurements. So basically, you can say this is the expectation value of atom number at a particular point in time. So here's the time that we tilt the potential. And then there's for different interaction strengths, these are these different curves, we observe different dynamics, different time scales. And the first thing that I want you to see from this measurement in the first place is, so we start with 2 atoms more or less, so it's a little bit less, that's the preparation fidelity. We always end up with 1 atom. So basically, what's happening in this experiment, so we apply some repulsive interaction between the atoms, we end up with 1 atom remaining in the trap. And so why is that? So what happens when we apply some repulsive interactions? If the interaction is basically 0, the atoms both sit kind of on the ground vibrational level of this trap, and tunneling is quite weak because the energy is very low. But now we apply some repulsive interaction, so the energy is increased, which helps tunneling, which favors the tunneling. But as soon as one particle has left, the other one will be in the ground state and will be protected from further tunneling of the trap. Yeah? So that's how we can, in very simple ways, analyze this kind of behavior. We simply fit a simple exponential decay to this one particle leaving the trap. And this time, this decay constant that we fit, we plot as a function of magnetic field, which of course tunes the repulsion between the particles. It's kind of this measurement. So we apply some repulsive interaction, increase the energy from the ground state, such that tunneling occurs. Yeah? And what you can see here, at low magnetic field, the repulsion is very, very weak. We observe very long time scales on the order of a second. And then you see, as the magnetic field is increased, the tunneling time becomes shorter and shorter because the energy of the system is increased. Now, what's also plotted here is another curve. And this curve is some very nice calibration of our system, because what we do for this curve is we fill our trap not with 2 distinguishable particles, like the spin up and spin down, but we put in our trap 2 spin-polarized particles. They are non-interacting. And because they are fermions, they will occupy the 2 lowest vibrational levels in the trap. Yeah? And so while we tune the magnetic field, this system is not tuned. Yeah? And so this gives us a calibration measurement, because now what we see from this measurement, from these data here, this will be the tunneling time of this single atom in the first vibrational level of our potential. Yeah? And so this is on the order of 100 milliseconds. So that's how we tuned the tilt, that this is kind of in the medium range for us to be observed. Yeah? And now what you can see, and what's quite interesting, this particular system with 2 distinguishable particles, it will be first have a lower energy. That's why the tunneling time is longer. And then when the coupling strength diverges to infinity, then this system has the same tunneling dynamics as the spin polarized system. Yeah? And so this also means it will have the same energy. And in one dimension, it also has the same wave function square. That's why this system is called fermionized, right where the coupling strength diverges and where these tunneling times of these 2 systems are the same. And what you can also see in this graph here is that you can even go further and increase the energy of this system beyond the energy of 2 spin-polarized particles. Yeah? So you can make the repulsion between the 2 particles stronger than the Fermi repulsion between 2 identical particles. Yeah? And that's the so-called super-Tonks regime that was first prepared in this paper here with identical bosons. And so we are studying kind of the 2-particle analog here of the Tonks regime, which is the strongly interacting regime around this resonant interaction strength in G1D. Okay, so what you can see, and that's somehow what you should memorize, if I go right on this diverging coupling strength, I get the same energy for the 2 non-identical particles as for 2 identical particles. And if I go beyond, the energy grows even bigger. That's something we should remember for the upcoming measurements. But first of all, let me explain you why this should be the case. Yeah? That's actually some sketch that has been shown, for example, also by Christoph Nägel before, and also by Vladimir. So what we basically do is, what's plotted here is minus 1 over the one-dimensional coupling strength. It's kind of weird because units. But why we plot it this way is because we increase the repulsion as we go from left to right on this graph. So here is basically 0 repulsion. And then the repulsion increases more. And right on this axis where 1 over G1D becomes 0, that will be the resonant interaction strength. Yeah? And we increase more and more the repulsion as we go this way. So we start here with 0 interaction. So that's kind of our harmonic oscillator potential with harmonic oscillator levels. And now as we increase the repulsion, we change the magnetic field this way. And we increase basically all the energy levels by a little bit. And right here on resonance, we've increased the energy by 1 h bar omega in our trap. And if we go even further, all the way across this resonance, then we basically, something didn't shift right here. Yeah? We basically shifted all our energy levels by 2 h bar omega, and there will be new energy level with the same interaction strength. Again, 0 interaction strength will be the same one as this one, but as we tune our interaction strength continuously, we actually go to an excited state in this system in this way. Yes? We don't end up in the ground state of the system, but we end up in an excited state. That's the important thing to know. Yeah? So we increase the energy of these two atoms by 2 h bar omega, and we are no longer in the ground state of the system. So this is for two particles. For this, you can have either an exact calculation, 3D solution, for example, from this paper here, or you can simply also use, for all purposes that we are interested in here, simply Thomas Busch's derivation of the scattering of two particles in one dimension. They work perfectly fine for this case. And now we should go, with this kind of insight, go and add more particles than 2. Yeah, so this maybe I said already. So this will be, normally this is called the repulsive side, where G1D is positive, and it will be called the attractive side. But really, we make the system more and more attractive because we go to an excited branch in this energy level diagram. So this would be kind of the attractive case down here, but because we are in an excited state, it's still, the energy is still growing as we go to the attractive side of this resonance. That's something you should also keep in mind. So now, let's go back to this graph here, just to give you an idea what really happens. So these are these curves that I showed you before, where we said, okay, there's only one particle of the two particles tunneling, so we have one particle remaining. And so if we have weak interaction strength, so we have slow tunneling dynamics, we increase the repulsion, we get this curve, and you see these other data points here. These are the two identical particles, and you see the dynamics exactly the same. This is because if you draw the wave functions, this is the relative wave function between the two particles. So with this one, will be more or less looking, still almost looking like a non-interacting system, but the particles slightly repel each other. And right for this curve here, the wave functions look like this. So this will be the wave function of two identical fermions. So this every one of us can immediately calculate. And this will be the wave function corresponding to two distinguishable particles, but we have the same energy as the two identical fermions. And that's why the wave function looks almost the same, but the sign is flipped at the origin. OK. And then if you go even further, we recover this kind of wave function, which almost looks like the one of the second excited state in the harmonic potential. OK, so now let's go for more particles. This is now the simplest case that we can do is just add one extra particle. Yeah, it looks like it's a very simple problem. So we add one more particle here, and we can now ask the question: what's the probability for this spin down particle here to be the first particle to leave the trap if we tilt it? Yeah, whether this happens or this happens. And of course, very naturally, we'd always expect that somehow this guy up here, yeah, the majority particle should leave our trap first. Yeah, that's what we expect. And let's see what happens. That's what we plot here is the probability to have this minority particle leave first, so that we obtain this kind of a system. And this is plotting it again here as a function of interaction strength. And so this is kind of zero repulsion on this side. And as we go further to the right on this graph, it becomes more and more repulsive. Yeah? And in the middle here, this would be the case of infinite interaction strength. So what you can see here, as we increase the repulsion, we get some finite probability for this minority particle to tunnel first, which is kind of interesting. And it increases more and more. And if we go for very large repulsion, we obtain a probability of larger than 50% for this minority particle to tunnel, which is kind of weird. Yeah. So and also right on the resonance, if you kind of interpolate between these 2 points, you obtain something like 1/3. Yeah. And that's actually something one should expect, because right on this resonance, I told you the wave function should somehow look more or less between 2 non-identical particles should look the same as the one between identical particles. And so the energy of all these 3 particles should be about the same. And that's why the probability for each particle to leave the trap should be the same. Yeah? And so if we go even further, then somehow the minority particle has a preference to leave first. Yeah? This is kind of weird. We can try to do the same experiment with even more particles. For example, with 4 particles or 5 particles, where we each have 1 minority particle. So the extreme case would be this one. And these are the corresponding data here. What you can see is there's actually some dashed lines here where it doesn't work so well. But if we go all across the resonance, you can see that the probability for this minority particle to leave will still remain around 50%. And that's even more striking, because imagine, I mean, if you look at this picture and you want to try to remove the minority particle first, it doesn't look very intuitive that it should happen. But now what you can see really is the repulsion is so strong that that this still occurs. Yeah? And the last measurement on this series that I would like to show you now, this is all kind of strongly imbalanced system where there's only 1 minority particle. Yeah, you could think of this also like as a polaron problem if you were now to increase the number of majority particles more and more. But another system that we are interested in, that we studied in this way, was this a balanced system. So 2 spin up particles, 2 spin down particles. So that's this kind of the smallest spin balanced fermionic system that you can make somehow. And now we tilt the trap so much that there's only 2 particles remaining. And what we look at now is the probability of having a spin polarized system remaining. Basically, we remove 2 of the 4 particles, and we just count whether we have 2 spin ups or 2 spin downs or a mixture of both. Yeah. And of course, if you look at this kind of picture, and I were just to tilt this potential, you'd always argue there should always be 1 spin up and 1 spin down particle leaving. Yeah. And we should have a spin balanced system if we have 2 particles remaining. Yeah. So what's plotted here now, the data is now these blue points. And what you can see as we cross this resonance, go to very strong repulsion, there's about 60% probability of obtaining a spin polarized system. And this is for us a very clear manifestation of ferromagnetic correlations in the system. So somehow the different spins separate from each other, in this case now in energy, but this must immediately also have a consequence on the spatial distributions of the particles. Yeah? So what we really observe here is ferromagnetic correlations in this finite system, in a one-dimensional finite system. Yeah? And so somehow we have now we went around this proof that ferromagnetism should not be present in one-dimensional system just for the reason being that all the theories so far only took into account that you can go to G1D equals infinity, which will be this vertical line here. But if you can go beyond, yeah, create an excited state of the system, then you can still obtain ferromagnetic correlations. I mean, that's the finding of this experiment. And you can now, of course, ask the question, what does this really mean? Yeah? Do we really have kind of a tiny ferromagnet here? Yeah? And then just, I mean, the few points that one should kind of consider in the way one thinks about this. The first thing is the system that we prepare is obviously not the ground state. Yeah? And so, of course, many of these assumptions, I mean, you typically want to make the assumption that the system you look at is the ground state of the system. The second thing is this magnetic state occurs only kind of in the attractive regime of this confinement-induced resonance, not in on the repulsive side. But that's also kind of a consequence of the system not being in the ground state. And because the system is finite, yeah, there's no phase transition that occurs between this case where the system is kind of antiferromagnetic, where on every vibrational level there's exactly one spin up and one spin down. And the ferromagnetic case, there's no phase transition and just a crossover because it's a finite system. But of course, if you think of magnetism, you always think of phase transitions. And they're not present here in this system. Yeah? But what's also kind of important to remember is the system is, we can prepare the system in such a way that it's completely stable. Even though it's not the ground state, it will still be completely stable against any relaxation. And in that sense, you can still somehow call it a ferromagnet. Yeah? So we tried to observe the stability of the system. We couldn't go, for some reason, beyond about 0.6 seconds, but that's really long compared to the 1.5 kilohertz trap frequency in the axial direction that governs the dynamics of the system. Okay, so that's the part of repulsive interaction. Let me shortly go for the case of attractive interactions in this system. And there we look for correlated tunneling and Oddeven effect I told you already before. So this system is actually much more difficult to study. So now what we do is, let's take first of all two particles. We make the atoms attract each other. So we reduce the energy of the system. And so we get similar dynamics as I've shown you before. We start with two particles, and you look at the mean atom number. And the first thing I told you to look at when I showed you the dynamics for the repulsive case was that we will always have one atom remaining. Now, if I look at this curve here, you see very clearly it goes to 0. So the atom number now goes to 0. So we no longer have single particle tunneling in our system, yeah? Which complicates the situation quite a bit because now we have to always consider the tunneling of two particles at the same time somehow, yeah? So, and if we now change the attraction, so first this was kind of this blue curve here was relatively weak attraction. Now we make the attraction stronger. Yeah, then what happens? The system lives for longer times as we increase the attraction in the system. Yeah, so that's what you can see from these curves here. Yeah? But it's a little bit harder to analyze now because there's always two particles tunneling at the same time. So we don't have a very clear way how to think of this yet. But we try to analyze how exactly can we see now whether the two particles leave the trap together or whether they just leave one after the other. And we try to get some measurement on this. And that's basically what we can do is we can only count the number of particles remaining in the trap. Yeah? So basically we can, after some time, wait time, we can basically just count. There would be like, for example, this case would be both particles are still present in the trap. We can count, whether there's one particle left in the trap, or we can have the situation there's no particle left in the trap. But this could have happened in two ways. We could have first one particle leave and then the other one, or they could have left together. And now how to find out what's the real process that's happening? Do these two particles leave together, or do they leave just one after the other? So what we do for this purpose, we plot the probability of observing one single atom, so this case here, as a function of the expectation value, so the mean observed number of particles in the system. So we start basically here, so that would be in the beginning, initially, and then as time progresses, the mean number of particles is being reduced. And first, so this is kind of first uncorrelated tunneling, so basically zero attraction between the particles. And then, of course, the probability for observing one particle, so this case increases and then decreases again as we go for a zero number of particles, yeah, which makes sense. And so now if we increase the attraction strength between the particles, what happens is the probability of observing one particle goes down. So there's two different interaction strengths, and you can see for relatively strong interaction strength, we basically never observe a single particle in the trap, which tells us that the particles have to tunnel in pairs. Okay, so that's still relatively preliminary data, and we still have to figure out exactly what we can learn from this, but you can already see that we can observe somehow particles tunneling in pairs. And the last thing I would like to show you today is this odd-even effect I promised you, and there we basically would like to study how the energy of the system evolves as we add more than two particles. And what's plotted in this diagram, it's a little bit involved. So this is actually a plot for different atom numbers. And we measure now the time scale for a particle to leave the trap for two different cases, either for a non-interacting system or for an attractive system. And so the first point here, that's basically just one single particle. And so that's now the ratio of the time scale for an interacting system versus the time scale for a non-interacting system. And so for one single particle, if it's interacting, it doesn't matter because it can the energy will not be changed. But as you have two particles, and we make these two particles attract each other, then the time scale for tunneling is increased by 6 dB. So the stability of the system is increased by a large fraction already. As we add a third particle, the non-interacting system is of course again less stable, but the stability decreases compared to the two-particle case because this one single particle in the first vibrational level is not paired to any other one. And you can go on, so this will be like the even number of particles again, and you can go up. We did this up to 6 particles, and you can see then the stability of the system has almost increased by a factor of 10. So the time scale for tunneling is almost 10 times longer for the interacting system as compared to the non-interacting system. And I'm more or less done.
I'm pairing up with you.
Yes. Yeah. So here's the summary. First of all, we can prepare these few-fermion systems with quite good fidelity, and we have very nice control over both repulsive and attractive interactions. We can look at feminization of distinguishable particles. We can observe magnetic correlations in the repulsive few body systems. And we can observe correlated tunneling and an odd-even effect for attractive interactions. And with this, I would like to thank, first of all, my team for doing all this great work. Yeah? So they've been working really hard to make all of this possible. And I would like to thank you for your attention.